Welcome back to the Fundamentals of IPOS. This is session number 6. We had a nice little short session last time as we took a quick look at the system variables. Now we're coming back to our learning the language, and this is part 3 of that. So let's plunge in. All right, we've covered compiler control, comments and formatting, constants and variables, and now we have, unfortunately, a somewhat heavy topic, and that is math and logic. Of course, since all programs rely heavily on math and logic, it is pretty important. So let's go ahead and take a look at it. C programs can include 3 different categories of numeric operations. And of course, IPOS, being a C-derived language, has these same 3 categories. They are logical operations. Those are things that give a true or false answer rather than a number. Ordinary arithmetic, this is like addition, subtraction, multiplication, and division. These do give number answers. And then what are called individual bit manipulation operations. These are things that work with individual bits within a number rather than treating them as a number as a whole. And some operations apply to all 3 categories. To help you keep everything straight as we go along, I'm going to be putting symbols next to different topics, and they will sort of clue you in which of these 3 things applies. So we have everything, logical, arithmetic, and bitwise. And those are the symbols. So let's go on. We'll start with an everything. This applies to all 3 categories. All categories support basic assignment. Now, assignment is done with a single equal symbol. And I think you can understand this one. It's pretty obvious. Let me give you a few examples just to cement it. If I take a variable, h1, and I say h1 equals 100, I'm assigning the number 100, and that's a decimal 100, into variable h1. So that stores it within that variable. On the other hand, if I say h2 equals h1, that means I'm assigning the contents of variable h1 into variable h2, so it stores h1 and h2. And here's another one, h3 equals hexadecimal ff. That's 255 in decimal, so that is simply a numeric assignment. Takes hexadecimal ff, or 255 in decimal, and it stores it in variable h3. I think that's pretty clear. I think we're all pretty comfortable with that. It's very basic math. However, be aware, there are a few specialized forms of assignments, and we will encounter those later. But this is the general purpose one. Another topic to do with all 3 categories, and that is something called precedence. All operations in math and logic have a precedence level that determines their evaluation order and priority. What does that mean? It means if you set up a bunch of different operations that they have different priorities. Certain things get evaluated first, other things come later. When you took a math class and learned about algebra, for example, you learned about how to evaluate things as you work through an equation from left to right. You learned that certain things happen first and other things come later. The same thing is true in any programming language. For example, multiplication and division have a higher priority than addition and subtraction, so they get evaluated first. Let me give you an example. Here's an equation. h1 equals h2 plus h3 times h4 minus 18 divided by h10. The question is, which operations happen first? How would this expression evaluate? All right, that could be pretty challenging to figure that out. And if you want to understand how IPOS handles evaluation precedence, then what you need to do is get into the manual on page 194, and it explains precedence and shows a complete list. But I'm going to give you a much simpler solution rather than trying to figure out what that does. Do this instead. Just use parentheses. If you use parentheses in an expression, they guarantee a specific order of evaluation. If you set up your parentheses right, that expression evaluates exactly as you want. So for example, if I want to make this same expression get evaluated in a very specific way, I can throw in some parentheses. And so now let me tell you what's going to happen. First of all, H2 will be added to H3. H4 will have 18 subtracted from it. Then those two results will be multiplied together, and then finally they'll be divided by H10. And the same rules that apply in ordinary math apply here. So that is my opinion. It's smarter just to use parentheses. It is never wrong to use parentheses. Just one little caution: mismatched parentheses are a common cause of compile time errors. So count your left parentheses, count your right parentheses, make sure you've got the same number, make sure they're in the right place, and everything will be wonderful. All right, moving on to our next category of math operation, and that is a logical operation. Many operations care only if something is true or false. They don't want a numeric answer, they just want a yes-no kind of answer. Now, in the C language, false is defined as 0, and true is anything that isn't 0. So 105 would be considered true. However, a lot of programmers like to think of true and false as 1 and 0. So many programmers just stick with 1 and 0 and treat those as true and false. And to make that easier in their code, they often define two constants called false and true, and they assign them to 0 and 1, and they just use false and true throughout their code instead of 0 and 1. And that makes it more readable, and then there's no question about what's what. There are three logical mathematical operations, and they are not, which is represented by an exclamation point, and, which is represented by two ampersand symbols with no space between them, and or, which is represented by two vertical pipe symbols with no space between them. Now, the not operation simply takes a logical value and flips it to the opposite. So if it's true, it becomes false. If it's false, it becomes true. An AND operation takes two values that are either true or false, compares them together, and if they are both true, in other words, everything is true, it outputs a true. And if even one thing is false, it outputs a false. Or basically says if anything is true, it will give you a true. The only way you'll ever get a false out of an OR expression is if they are both false. Let me show you some concrete examples if that wasn't entirely clear. All right, we have some variables here. We have H1 and H2, and we put a false in H1 by putting a 0 in it, and we put a 1 in H2, which makes it true. And if I say H3 is not H1, I use that not operator, that means flip it. Now, H1 is already false, so when we not it, it becomes true. So H3 now has a true in it. If I say H4 is H1 ANDed with H2, that means I take H1 and H2. They both have to be true for that AND to give back a true. But they're not. H1 is false. So H4 will contain a false, because that's how the AND operation evaluates. On the other hand, if I OR H1 and H2, since H2 is true, then I'm going to get a true out of that, and H5 will now have a true in it. Okay, now we come to the familiar kind of arithmetic, addition, subtraction, multiplication, division type math. Need to talk about a few details associated with it before we look at the specific operators. Just a reminder, all arithmetic operations are signed operations. They always operate on 32 bits, so there's always a sign in the picture when you do conventional arithmetic. If you supply decimal numbers, remember they will always be sign extended so they fit into a full 32 bits. For example, if you say H1 equals 17, that's actually plus 17 decimal. And this is what will be sitting in there. If you looked at the individual bits, there will be a full 32 bits. And since it's a positive number, the sign bit gets sign extended all the way to the most significant bit end. On the other hand, if you say H1 equals minus 9, which is a small negative number, it's going to do this. It's going to sign extend using 1 bits. Of course, do remember if you supply small binary or hexadecimal number, they will always be padded with zeros, in other words, treated as positive. So if you want to encode a negative number in hexadecimal or binary, be sure to supply the full 32 bits, either 32 bits of binary or 8 hexadecimal digits. Otherwise, they'll be treated as positive and you will get some unexpected results. And then finally, one very important point, all arithmetic operations are integer. In other words, they operate on whole numbers. There is no fractional component. There is no rounding. It simply drops any fractions silently. Bear all this information in mind so you get the math results that you expect. Here are the arithmetic operations available in IPOS. Addition, subtraction, multiplication, and division. That should be familiar. But there's one more you might not be acquainted with. Use a percent symbol for it, and that is remainder. That will do a division, and instead of giving you the quotient, it will give you the remainder if there is one. So you can use that to sort of work around the fact there are no fractions, because you can at least compute the remainder and maybe then work with that in some way. Let me show you a few examples. If I take H1 and put a 10 in it, and H2 and put a 4 in it, I'll do some math with it and we can see what we get. If I say H3 is H1 plus H2, that's 10 plus 4. That gives us 14. No surprise there. If I say H4 equals H1 minus H2, then it's going to be 10 minus 4, and that's 6. Again, no big surprise. But if I say H5 is H2 minus H1, that is 4 minus 10, there will be a minus 6 in H5. That's pretty smooth sailing. Now if I change the values, so I've got a 20 in H1 and a 3 in H2. If I say H3 is H1 times H2, that's 20 times 3, there will be a 60 in H3. I say H4 equals H1 divided by H2, that's 20 divided by 3, and that does not give a nice, neat answer. It gives a 6, and normally there would be a fractional part, but remember we don't get fractions, so we just get a 6 in there. If you want to know what's left over, though, you can do this. You can take H5 and say it equals H1 remainder H2. That does the division, but instead of giving the quotient, which is 6, it gives the remainder, which is 2. Pretty clever. There are two very handy arithmetic operations that don't require the usual assignment style structure. In other words, they don't require you to use that equal sign to assign something. Let me show you these. This is a traditional assignment style operation. Let's say I want to take H1 and just increase it by 1. I would say H1 equals H1 plus 1. That's called incrementing. And if I want to do the opposite, I could say H1 equals H1 minus 1. That is called decrementing, when you decrease something by 1. These allow you to increment or decrement a variable in one easy operation. You just say H1 plus plus. No spaces in any of that, and don't forget the semicolon. Or H1 minus minus. That's exactly the same thing, so it's a handy little shortcut. There are also some assignments that are combined with operators, so they sort of do two things at once. Let me point these out. Plus equal, that adds and assigns. The destination is always part of the operation. What do I mean by that? Well, let's look at some comparisons here. If I say H1 plus equal H2, that is the same thing as H1 equals H1 plus H2. So in other words, H1 always is involved with this. So the destination, where it goes when you're done, is also part of the operation. H1 minus equal H2 is the same as H1 equals H1 minus H2. h1 multiply equal h2 is the same as h1 equals h1 times h2. h1 divided equal h2 does the same thing as h1 equals h1 divided by h2. And h1 remainder equal h2 is the same thing as h1 equals h1 remainder h2. So you can use these if you like. Some programmers avoid them because they think they make their code not quite as readable. I don't tend to use them in my code, but they're there if you'd like. So do what you like there. All right, we move on to our last category in math and logic, and that is bitwise operations. What do I mean by bitwise? Bitwise operations allow you to work with the individual bits that make up a variable. In control scenarios, we do a lot with individual bits. Many Movi Drive B operations involve what's called setting and clearing bits to control the drive. Setting means changing a bit to a 1. Clearing means changing it to a 0. So by turning bits on and off, setting and clearing them, we make things happen, like make the drive start or stop. We also use bitwise operations to examine individual bits within a variable. Maybe we want to see if a particular I/O bit is on or off, or we want to go into one of those system variables like the status system variable and find out if the magnetic field is turning. We can do that by looking at the right bit and then querying that bit and finding out if it's 1 or 0. So checking status involves monitoring individual bits. So these are the kind of things we do a lot. So the bitwise operations help us do it. Let's look at a few of these. The first bitwise operation is called invert. It simply flips all the bits in a variable to the opposite value. So the 1s become 0s and the 0s become 1s. Here's an example. Let's say we have this value and we say invert it. You can see everything is just changing to its opposite. So there you go. That's an inversion. Pretty simple. And we have AND. Now this is sort of like the logical AND, but what it does, it compares two variables bit by bit. Both bits are 1, it outputs a 1 in that position, otherwise a 0. Remember, AND wants to have everything true. So let's look at an example here. Let's say we AND these two numbers together. What we do is we compare bits in the same position with each other, and that gives us our output. So we start here, we take 1 and we compare it with 1. They're both 1s, so we output a 1. Same thing here, they're both 1s, so again we output a 1. But here we have a 0 and a 1, so that gives us a 0. We have a 1 and a 0, that gives us a 0. We have a 0 and a 0, that gives us a 0. A 1 and a 0 gives a 0. A 0 and a 0 gives a 0. And a 1 and a 0 gives a 0. So there we go. An OR operation does exactly the same thing. However, if either bit is 1, it outputs a 1. Otherwise, only if both bits are 0 will you get a 0. Let's see an example of this. So we have these two numbers. We're going to OR them together. So we start with the first bit, 1 and 1. We compare them together. They're both 1s, so we get a 1 from that. We have again two 1s. That gives us a 1. We have a 0 and a 1. And of course, that gives us a 1 because remember, you just have to have at least 1 in there. You don't have to have them all like you do with AND. 1 and a 0 gives us a 1. Now here we do have two 0s, and so of course they will give a 0. We have a 1 and a 0, that gives us a 1. Two 0s, again we get a 0. And then finally a 1 and a 0, we get a 1. So that's a bitwise operation, bit by bit going through two variables. So we can do that by ANDing or ORing. And now we're going to look at a bitwise function that maybe you've never heard of before unless you've been programming for a while. And that is something called exclusive OR, which is usually abbreviated XOR. And this is kind of an interesting version of OR. It again compares the numbers bit by bit, and if one bit is 1, it gives you a 1. But if they're both 1 or both 0, you get a 0. So it's kind of a slightly different sort of OR. Let's see an example. We'll take these two numbers, we'll exclusive OR them with each other. So we have a 1 and a 1, so that gives us 0 because you don't want both to be 1. Another 1 and a 1 gives you a 0. But a 0 and a 1 is fine, that gives us a 1. A 1 and a 0 is fine, that gives us a 1. 2 zeros, nope, get a 0 out of that. 1 and a 0, no problem, gives a 1. 2 zeros, no way, gives a 0. And then 1 and a 0, that gives a 1. So that is exclusive OR. That one may seem a little strange to you, but it's actually extremely handy, and in a little while you'll see how it's used. Now we come to a bitwise operation that you might not be familiar with unless you've been programming for a while, and that is the shift operations. These take individual bits within a variable and they shift them either to the left or to the right. In control applications, this is extremely useful. You see it done all the time. There are two shifts, and you can guess what they are. One is shift right, as we're showing here. The other is shift left. We're going to take a look at both of these. The two operations do differ very slightly. With the shift right operation, bits are shoved down from the most significant bit end. The least significant bit is just pushed off the end. It kind of falls off the table and is discarded. So what's on the right falls off and goes away. But on the left side, the sign bit, whichever it is, remember it's going to be 1 or 0, depending if it's a positive or negative number, it gets replicated on the left side, on the most significant bit side. So if you do a bunch of shifts, then you're going to have that sign bit replicated a whole bunch of times. Let me demonstrate this happening. And to do this, I've got to show a full 32-bit number. I can just barely fit this on the screen. We'll start with the number here on the left. You notice I've underlined the sign bit. This is a positive number. It's got a 0 sign bit. And I've specified we're going to shift it right 3 times. When you shift, you always say how many shifts you want it to do. So we're going to shift it 3 times, which means that the bits are going to move from left to right. The least significant bit will fall off the table, and the most significant bit, which is the sign bit, will get replicated. So watch it closely as we move the bits. You'll see it happening on the number that's on the right side of the screen. Here we go. Here's our first shift. Notice we duplicate the sign bit, and if you look at the least significant bit end, that's shifted down by 1. Here's another shift. Here's a third shift. You can see those bits have all moved down, and the sign bit's been duplicated 3 times. Let me show you this same operation with a negative number. We have a 1 sign bit here. We're going to do the same thing, shift it 3 times to the right. So watch the 1 bit. You notice it gets duplicated. Of course, at the other end, the same thing happens. The bits move down and the least significant bit falls off the table. There's 2 more shifts and we're done. That's shift right. Now you might think shift left is similar, but actually it's a little bit different. The bits are shifted left, moving from the least significant bit end to the most significant. Of course, that's obviously different. But the sign bit does not get preserved. It just gets corrupted. And zeros always come in on the right side. So zeros come in on the right, the left side falls off the end of the table. It doesn't do anything to protect the sign bit. Let me demonstrate this again. We'll use the same numbers, but we'll shift them left 3 times. So watch the bits closely. Notice that we have zeros coming in at the least significant bit end, and everything just gets shoved down, and the most significant bit drops off the table, and that's the end of it. So if we had some 1s at that end, those could get shoved into the sign bit and cause it to change from positive to negative. But do remember, in most control situations, we're really not thinking about the sign. We're just interested in bits as bits. Let's see this happen with a negative number just for illustration. We'll take our negative number here. We'll shift it left 3 times. So 1, 2, 3. You can see again, the most significant bits just go off the table. The sign bits are gone. This number is now a positive number if we care about that, and we have 3 new zeros on the right side. There we go, shift right, shift left. Kind of interesting. You will definitely see them in the near future. Let me give you a new term, and that is bit manipulation. Bit manipulation means you're changing individual bits within a variable. So for example, if we want to change a bit to make the motor start, we would use a bit manipulation technique. Or if we want to turn a digital output on or off, we would use a bit manipulation technique. And that would cause just one bit within that variable to change. Now there are 3 things you can do to a bit when you're manipulating it. You can set it or clear it. That means make it 1 or 0. But then there's a third thing you can do, and that is called toggling. What toggling means is change it to its opposite. So if it's a 0, it becomes a 1. If it's a 1, it becomes a 0. And that is very handy, believe me. So a bit manipulation operation affects only the targeted bits. It doesn't mess with any of the others. So let's look at an example. Let's say we want to mess with memory location H480. That is the option card output. So if you've got an expansion I/O card in your Movi Drive B and you want to cause the digital outputs to change, you would bit manipulate this location and it would cause changes. And just to review, bit 0 is the least significant bit. It's on the right side. Bit 31 is the most significant bit. It's on the left. And digital output 10 through 17 are the bottom 8 bits. All right, let's do a little bit manipulation. Let us say our goal is to turn DO13 and DO15 on. We want to set those bits. So here are the bits in question. We want to change those two so they're on. We want to set them. The way you do it is you OR it with a binary number that has a 1 in each position that you want to turn on. So we create a binary number here and we put 1s only in the locations that we wish to switch on and 0s everywhere else. So we OR H480 with that number, and here's what happens. Those 2 bits go on. If you had lights attached to them, they'd light up as soon as you did this. So that's how you set bits, by ORing with 1s. Now let's say we want to do the opposite. Let's say we want to clear some bits, turn them off. We'll do some different bits. Let's do DO11 and DO16. These are the 2 bits of interest. You turn things off with an AND operation, and you put 0s where you want to turn the bits off and 1s everywhere else. So kind of an opposite thing you do. And you notice here, those 2 bits obediently go off, but notice all the other bits didn't get touched. The ones that were on are still on, and the ones that were off are still off. That is the beauty of bit manipulation. It only changes what you want to change. It leaves everything else intact. Now, what if we want to toggle some bits, flip them to the opposite? You often use toggling to produce blinking lights, where you want a light just to cycle on and off. You just keep toggling it. Let's say we want to toggle DO10 and DO17. These 2 bits. You can probably guess which operation we're going to use for this. We've used AND, we've used OR. We're going to use exclusive OR now. This is one of its major uses. What you do is you put a 1 in every position you wish to toggle, and you put 0s anywhere you want to leave alone. So we exclusive OR H480 with this bit pattern, and you can see the 1 bit became a 0 and the 0 became a 1. And that's pretty nifty. Another kind of bitwise operation is bit testing to determine the value of specific bits within a variable. For example, maybe you want to read some switches attached to a digital input port, and you want to find out if those switches are on or off. You use bit testing operations to do that. Now, to test individual bits, you have to do something called masking. You're going to mask off the bits that you are not interested in. And that way you'll only see the bits you care about. Let me show you. Let's say we want to read H520, input level B. This allows us to read our digital inputs on our Movi Drive B. So the built-in digital inputs, DI00 through DI07, are the bottom 8 bits. And then if you have an expansion card installed with DI10 through DI17, they are the next 8 bits. So to read these, we mask off everything we're not interested in, and that leaves behind the ones we care about. Let's look at an example. Let's say we want to find out if DI03 is on or off. That's this bit right here. You AND it with a mask. And here's what the mask is. It's got a 1 in the position of the bit you care about and zeros everywhere else. Those zeros block off the things you aren't interested in, and the 1 will let through the bit you do care about. So when you AND this is what comes back. That bit was off, and so this is off. So see, the blue bit matches. That's the one that shows you what's in DI03, and you can see it's off. So if the result is 0, that's hexadecimal 0. I did that because I didn't have room to write 32 bits. DI03 is off. Let's look at another one where it's on. Let's say I want to determine the value of DI06. That's this one, which happens to be on. I do exactly the same thing. Of course, I have to change my mask to put that 1 bit in the right location. So what I do is I AND it with the mask, and it comes back like this. There is a 1 in that location where the blue 1 is. That happens to be hexadecimal 40. So if I get a hexadecimal 40 back, DI06 must be on. Now that's a little clunky, having to convert all those numbers and figure out what the different hexadecimal or binary values are. So guess what? There is a better way, a simpler way. And we use another bitwise operation to do that. We do this. We do exactly the same thing. We create a mask, we AND it with what we're interested in, but before looking at that number, we do one extra thing. We shift right, in this case, 6 times, because we want to shift the bit we care about to the least significant bit position, and that takes 6 shifts for this particular one. So kind of like that, boom, 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 boom. And now there's a 1 down there, and the answer is either 0 or 1. If it's 0, the bit's off. If it's 1, the bit's on. So I recommend creating a mask, ANDing it, and shifting. Of course, you do have to shift right the number of times. In this case, 6. So do be aware of that. You will see some code illustrating this principle at work. Now, these are the bitwise operations that are available. We have inversion. This is the tilde symbol. It's near the 1 key on your keyboard. It's to the left of it usually. The AND operation, which is a single ampersand, OR, which is a single vertical pipe, exclusive OR, which is that symbol you sometimes use for exponents, or some people call it the caret. Shift right is 2 symbols pointing in that direction, no space between them. These are greater than and less than kind of symbols. And shift left, opposite symbols pointing the other way. Notice they look like arrows pointing the direction of the shift. That's a good way to remember them. Just be sure you don't put a space between them. Let's see a few quick examples. And I'm using binary numbers here because we want to actually watch the bits. So here's H1 and H2. If I say H3 equals invert H1 or not H1, all the bits flip. So if you look at H1, you can see that what's in H3 is just the same number with all the bits flipped to the opposite state. If I say H4 is H1 and H2, then I take those and bit by bit I compare them using the rule of AND where they both have to be 1. And you can see the only bit that managed to get through was the most significant bit because there were 2 1s in that position. Everything else did not have 2 1s. So we got 1 0 0 0. or of course is a little more tolerant. Everything got through here because we had at least one bit in each position. Let's do an exclusive OR. Remember, with exclusive OR, you can only have a single 1 bit for it to come through. And so that happened on 3 of those, but the 2 1s in the most significant bit position did not get through. That gave a 0. Let's take a look at the shift operations. First of all, we'll do a shift right. So we have 2 greater than symbols together, no space between them, and the number 2 after it, which indicates we're going to do 2 shifts to the right. We're taking variable h1, we're shifting it and putting it in h4. Let me remind you of something here. We have supplied a very small binary number, just 1010. When you do that, you have not supplied a full 32 bits, so IPOS simply pads it with zeros. In other words, it's treating it as a positive number. Therefore, when it shifts, what it's going to replicate is the positive or 0 sign bit. That means that when it's shifted, it's just going to move down 2, and we're going to have 0010 in there, so that right shift goes that way. We'll do a left shift of 2, and you can see that zeros come in on the right side, the least significant bit side. Everything moves down toward the left, and of course, if we could see at the very end, those zeros would also be falling off the table. Remember, there will be zeros down there because this is a small binary number. It's been padded with zeros and therefore is positive. Okay, hope that made sense. A little warning here. Be very, 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 very careful. Do not confuse not, double and, double pipe, which is not and or, the logical operations, with the tilde, single ampersand, single pipe, the bitwise invert, and or operations. I know they have the same name, they look similar, but you will get different results. If you're just doing simple logic, use the exclamation point, the double ampersand, and the double pipe. If you're doing bitwise, use the tilde, the single ampersand, and the single pipe. I know that's a little confusing, and it's a very common mistake with new C programmers that they use the wrong one. All right, now let's tackle a very important key idea that has some wide-ranging implications. I've said this before, but I'm going to say it again. In IPOS, all numbers are integers, so math operations don't generate fractions. There are many situations where fractions are very important. And the question is, in an integer-only world, how do you deal with that? There are several strategies for doing calculations that involve fractions using only integers. I'm going to show you one possible method. It isn't necessarily the best way or the most accurate, but it's easy to understand and it keeps your code relatively readable. But I would just say as you become more experienced with this or you do some reading to see how other people handle this topic, feel free to develop your own methods. That is always true in programming. All right, so let's look at one possible method, and I'm going to use something as an illustration to kind of work our way into this. I'm going to say that we're trying to connect a temperature probe to our Movi Drive B. Now, this particular temperature probe has a temperature range from 0 to 275 degrees C. It outputs between 0 and 5 volts across that range. So if you do the math, that basically says that for every millivolt the probe puts out, that represents 0.055 degrees C. Now, why did I say millivolts instead of volts? Well, it's really simple. The Movi Drive B reports millivolts when you connect something up to one of its analog inputs. So it's better to work with those. All right, now here's the goal. I want to read the sensor, convert the voltage into degrees C, and then convert degrees C to degrees F. So we have a Fahrenheit rather than Celsius temperature reading. So this is going to involve 2 calculations. One to convert the voltage to a temperature, and then one to convert the temperature. So these are the 2 formulas that we would use for this. We would first take the voltage coming in and multiply it by 0.055. That would give us our temperature in Celsius. And then we'd use the classic Celsius to Fahrenheit conversion formula, 1.8 times Tc plus 32. So let's do an example the way it would work if we just did it on a calculator. Let's say our probe outputs 1873 millivolts. That voltage represents the temperature. So we pull out our pocket calculator and we take 0.055 times 1873, and that gives us 103.015 degrees C. All right, no problem there. Then we convert it to Fahrenheit by taking 1.8 times 103.015. We multiply those, we add 32, and we get 217.427 degrees Fahrenheit. Now that's plain sailing, and if IPOS could work with fractions, if it had, for example, a floating point data type, we could just do this and we'd be done. But unfortunately, it does not. It only works with integers. And just a heads up, you don't want to just do an approximation with integers. You'll get answers that are pretty far off. Okay, you do really need to try to implement the fractions in some way. So how are we going to handle this? Well, let me show you a way we can do this with just integers. We're going to take our two formulas and notice that we have two fractions in here. We have that 0.055 and that 1.8. Now what we want to do is get rid of those and change those into integers. And so here's what we're going to do. We're going to multiply the equations by powers of 10 to get rid of the fractions. Essentially what we're doing is shifting the decimal place enough places over to turn that fraction into an integer. Now of course we've got to obey the rules of math and we need to do it to the whole equation. And when we're all done with the math, then we will divide that back out. And that will give us then an answer that's appropriate. So let's see this in action. So for example, for our first one, we've got 0.055. If we multiply that by 1,000, that will turn it into 55. So we now have a new formula. Tc equals 55 times the input voltage, and then we divide out the correction. We divide out that 1,000. So when we're done, our math will have been done sort of with a fake fraction. And when we're done, it'll come back. We'll have an integer, and it will basically be pretty close. All right, now for the second formula, Fahrenheit to Celsius, we have the 1.8. We only have to shift that decimal place one position. So we'll just multiply it by 10. So we multiply the expression in parentheses by 10 and also the 32 by 10. And that gives us our new formula. And of course, when we're all done, we divide the 10 back out. So let's see this at work, actually prove this works. Let's say that the Movi Drive B reads 2,084 millivolts from the temperature probe. So it's going to crunch that number using our special adapted formulas. So we take 55 times 2,084. And then we divide by 1,000, and that gives us an integer answer of 114 degrees C. Okay, not too bad. And then we do our Fahrenheit conversion. We take 18 times 114 plus 320, and then when we're all done, we divide it by 10 to remove the shift, and that gives us 237 degrees Fahrenheit. So not too bad. It's not perfect, and it won't necessarily give you the most deadly accuracy, but it's pretty close. So this is one method that you can use in a lot of applications, and I rather like this method. Now, a little warning here. Operation order really does matter when you're using this technique, because remember, you are doing integer math. If you do an intermediate calculation that gives a non-zero number less than 1, in other words, you get what would be a small fraction less than 1, it's just going to become 0. And if you drop a 0 into an equation, it's going to affect all the subsequent calculations in some way. So this can really bite you if you're not careful. So you need to sort of think ahead when you're setting this up. Let me give you an example. Let's just take a very simple formula. A equals B divided by C times D. And let's say we have some numbers like B is 1,024, C is 10,000, and D is 150. If I calculate in this order using integer math, I take 1,024 divided by 10,000, that would normally be a fraction. But since we don't have fractions, it just goes to 0. And then 0 times 150 is 0. And that is very definitely not even close to the right answer. See, we allowed ourselves to get into a calculation that resolved to 0. But if we change the order of operations, we can avoid this. If we take 1,024 times 150 and then divide by 10,000, we get the answer 15, which is actually correct. These are both mathematically identical expressions, but they don't give the same result. And the reason they don't is because we've got integer math that can't handle fractions. So you need to sort of think ahead how you do your math, and especially when you remove the correction by dividing that power of 10 back out. In fact, sometimes it is smarter to leave it in there if you're doing a sequence of calculations and not divide it out until the very end. Of course, you've got to keep track of things and make sure you divide the right power of 10 out. And that's where you've got to kind of put your math thinking cap on to be sure you're preserving the rules of math. Remember what they teach you in algebra. Always do the same thing to both sides of an equation. Never unbalance the equation. Okay, that's something you have to remember. A good way to really cement this in our mind is to do a hands-on task. So we're going to do actually a rather challenging program. This is a new program number 3, so you will need to save your old source file, get rid of it, switch to a fresh one, program 3. So let's kind of work our way into what we're trying to do, and then I'll tell you what you need to actually do. Let's say we are developing the math for a positioning conveyor run by a servo gear motor. This is a common application where a servo motor is connected to a gearbox and it's driving a conveyor. And so you're positioning things on that conveyor. You want to move that belt back and forth by specific distances. And so you're going to want to put in distances in units like millimeters and have that belt move. But of course, to make that work right, you've got to kind of translate that into rotations of the motor. So what you need to do is translate the distance the belt should move into increments that the motor must turn to produce that motion. Because remember, as that encoder turns, it outputs increments, and we count those to know how much the motor's turning. So that's what we're really up to here. We're developing some math. And we've got this little extra complication. When you throw a gearbox in there, which is usually going to reduce the output speed of the motor, that actually multiplies the number of increments required to produce the motion. In other words, you've got to take that gearbox ratio and multiply how many increments you need by that ratio. You're going to need to generate more increments because that gearbox is acting as a reducer. So that's an added little wrinkle to this, but that's okay. It makes it more fun. Here's the gearbox we're actually using. This is a real SEW gearbox and ratio. This is an S37. The ratio is 5.38, so very definitely a fractional ratio. It's not just a simple integer, so we've got to handle that 0.38 that's in there with the 5. So let's talk about kind of the theory of positioning. All right, this is a classic roller conveyor. We have 2 rollers with a belt, and the rollers have a diameter. In this case, we'll say it's 104 millimeters, and that's going to be connected up to the motor. The motor's turning it, and that's translating rotary motion into linear motion. And that's really what we need to sort of work out first. How do you relate rotary motion to linear? We can measure our rotary motion with the motor encoder. And remember, all motor encoders on a MoviDrive B output 4,096 increments for one complete motor shaft rotation. So that is always true. Let's kind of look at the math here. The first formula we need to work with is a very familiar one. It's one you probably learned in grade school. It's the circumference formula. We calculate the circumference of the roller by multiplying pi times the diameter of the roller. So in this case, we have a 104 millimeter roller. If we multiply that by pi, it will give us the circumference. So that's the linear distance that if you turn it one complete rotation, that will cause the belt to move an equal distance. Don't forget, of course, that pi needs to be brought into this, and we'll just say 3.14 is fine for now. We don't need tons of decimal places here. So basically, one roller turn is going to move the belt the circumference distance. So if we turn that motor one rotation or 4,096 increments, then the belt is going to move a distance equal to the circumference. That's an important idea. You'll be using that a lot if you do any positioning programming, which I'm sure you're going to do. However, we've got a little gotcha here. Remember, we've got that gearbox, and that gearbox slows the motor down. So the motor's got to turn more rotations to move that distance. So we need to calculate a scale factor that incorporates the motor encoder's resolution and the gearbox's ratio. So our encoder's scale factor is the gear ratio, which in this case is 5.38, multiplied by the encoder's resolution, which is in increments per revolution. So it's 5.38 times 4,096. That tells us how much we have to turn. Now we'll calculate a positioning scale factor, and we do this by taking that encoder's scale factor, divide by the circumference of the roller. That'll give us a scale factor that can translate distance to increments. And then when we want to actually make things move, we just take the distance we want to move in millimeters, multiply it by position scale factor, and out will pop a number that's the number of increments that we need to count from that encoder to move that distance. Pretty simple, but you can see there's definitely some fraction math going on here. Let's look at the actual numbers. All right, we can calculate the circumference of the roller here. It's 104 millimeters times 3.14. That's 326.56. So that is the linear distance one rotation of the roller will move. So the belt's going to move that amount if we turn that roller one rotation. Now, the encoder scale. We need to multiply 5.38 times 4,096. So that gives us 22,036.48 increments per revolution. So that's our encoder scale factor. And no, you don't want to round that off, even though you can't have a fraction of an increment, because we need to keep our fractions through the calculations until the very end. Otherwise, we're going to get rounding problems and our positioning will be less than accurate. So we keep all our fractions at this point. Now, our positioning scale, remember, is just the encoder scale divided by the circumference. So we take 22,036.48, divide by 326.56, and we get 67.48 increments per millimeter. So in other words, if we want to move 1 millimeter on that belt, we need to turn the motor on and count 67.48 increments, or probably just 67. Since we can't go a fraction of an increment. Okay, so that's our math. Now, let's say I tell the belt, move 1,200 millimeters. So I take 1,200 times 67.48, and that says move 80,976 increments. And notice here, I finally just drop my fraction, because truth is you can only move an integer number of increments. So that is the amount I move, and that should move the belt the right amount. And that takes care of the gearbox and all the other factors. Okay, so you can see we need to keep our fractions in there up until the very end. So this is what you're going to do for your program now. We're not actually going to make anything move. We're just creating the math at this stage. I want you to create a program where the application parameters are constants. That means like the roller diameter, the encoder resolution, the gearbox ratio, those should be constants. So later, if somebody wants to change things, they just have to fix a few constants. They don't have to dig into the code. Then I would like you to create a named variable called distance. In other words, use the long keyword. So IPOS will automatically assign an H variable. So create one called distance. Then create some additional named variables with matching equations, sort of like what we just looked at. Create one for circumference, the encoder scale, position scale, and increments. And I'd like you to handle fractions using the techniques that you've seen me demonstrate. You may want to go back and review some of that. And just do 2 decimal places for all numbers. And for pi, use 3.14. So do everything to 2 decimal places. That's accurate enough for this. And I would suggest don't divide out the decimal place shift value until you come to the very end. Otherwise, you're going to get some rounding and your program won't be quite as good. Now, once you've coded that, run the program, and it's just going to run over and over and over and do that math constantly. Pop up the All Variables debugging tool, find distance, change it to 1200. And that will force it then to compute based on a distance of 1200 millimeters. And then using the All Variables window, you can look at the other variables and make sure they change to appropriate values, particularly increments, which should change to 80,976 or something pretty close. If you code it slightly different, you might get a slightly different number, but you should be pretty close. Okay, go ahead and pause the video. Give it a try. This is a fairly hefty challenge, but I'm sure you're up to it. And then when you're done, unpause, and I'll demonstrate how I solved it. All right, well, let's see how you did. I will show you my code, and you can compare it to yours. And if you really struggled with this, hopefully this will help you see how to make it work. Okay, well, we're moving into something a little more challenging. When we get involved with math and we have to kind of create these sort of pseudo fractions, it's definitely a notch up in challenge factor. So if you struggled with this or even didn't succeed with it, don't feel too bad. I definitely threw you a more challenging program than is typical. So I'm going to show you how to solve this, and I'm going to show you how to work around a little gotcha that maybe caught you. So let's get going. First of all, of course, we have to change our source program. We still have program 2 up, and so I'm going to do a save as to program 3 just to give us that new program as specified. And I'm going to close this window. I'm going to expand the source modules and remove program 2 from the project, and then add program 3 in its place, open it up. And of course, like a good programmer, I'm going to update my comment section right away. And this is going to be positioning conveyor math. All right. Now I'm going to delete all this code in here because we're not reusing any of this. So I'm just going to kind of clean out most of this. Of course, I suppose I could have just gone and created a new skeleton, but this is okay. So there we go. So we're now ready to get going. Now remember, we're really not doing any positioning. We're just creating the math that does the computations, and we have to try to maintain 2 decimal places of precision as we go along. So we're going to build this step by step. Now the first thing that is a smart thing to do is to create the constants that should be in the program. Remember, the instructions said that all the application parameters, like the roller diameter, the encoder resolution, and the gearbox ratio, should be constants so that they can be changed easily if the machine changes. We're also going to define pi as a constant because we need pi for calculations. So I'm going to cut and paste the 4 constants that are necessary here just to save time. So there they are. Let me just explain these. All right, we have the roller diameter. So I create a constant called diameter. Remember, all uppercase for constants. I defined it as 104, so it's 104 millimeters. Then I defined pi as 314. That's actually 3.14 times 100. That's how we're going to get those 2 decimals of precision. So we use a shift factor of 100. Our encoder resolution is 4,096 increments per revolution. And our gear ratio, which is 5.38, is also multiplied by 100 to give us a nice, neat integer of 538. Notice I have taken the trouble to comment all of these, and I've even explained that for some of them I've multiplied them by 100. This is smart because this kind of fraction math isn't super obvious, and if someone reading this down the road has never done this kind of approach to fractions, it might be really confusing. So I've given them sort of some assistance by writing some good comments. All right. So that takes care of my constants. Now I'm going to need some variables. And rather than using pound define and picking h numbers, I'm going to let IPOS just pick the h numbers by using the long keyword. So I'm going to insert my variables, and there they are. I've got one for the distance I wish to travel, one for circumference, one for the encoder scale, one for the positioning scale, and one for the number of increments we have to turn. Notice I've just put them all on a single line there, and I've also commented that they're all positioning variables. All right, nothing too hefty so far. So that takes care of everything we need. Now we have to start writing some code here. We're going to have to do some basic calculations that are part of initialization. They're done only once. So we're going to put them outside the while loop, but inside main. That means they'll get executed once at startup and then never again. So we need to calculate the circumference of the roller, the encoder scale, and the positioning scale. And we sort of have already talked about how to do this, so we're just going to set these up as three equations. So let's take care of circumference first. So there we go. Circumference is pi times diameter. So this calculates the roller circumference. Notice again, I've commented this, so it's quite obvious what it does. Now we're going to calculate the encoder scale. So there's our encoder scale. So the encoder scale is the gear ratio times the encoder resolution. Notice, by the way, I am not dividing out those 100s that shifted the decimal place. If I did that, it's almost like rounding too early, and I would wind up with numbers that would be approximately right, but really wouldn't be as accurate as they could be. So I'm not going to divide out until we're all done. Now, lastly, we need position scale. So there we go. We're now going to take encoder scale divided by circumference, and that will give us our position scale. So that should take care of the basic math. So these will be calculated once at startup based on the application parameters and never again. Now the final calculation takes place inside the while loop because this is going to have to be calculated repeatedly as we go along. We have to calculate the number of increments to move for a given distance. So we're going to put in one final calculation here, right there. And I need to get my comments to line up. There we go. So increments is the distance times position scale. Now, this may not give us exactly what we want, but I think we're ready to go ahead and give it a trial run and see what happens. Remember, we're going to key in 1200 millimeters as our distance using the variables watch window, and we'll see how many increments we get. So let's first of all just compile our program and make sure we haven't made any mistakes. And we haven't. So we're going to now start the program. And I've got to open the variables watch window, so I'm just going to open the all variables window here. Now you notice we're not seeing distance, circumference, encoder scale, position scale, and increments up at the top. Remember, we've asked IPOS to pick the H variables, so we've got to go hunt for them. So I'm going to scroll slowly down until we find them. There they are. So IPOS started at 420. So we can see distance is 0, we can see circumference has been calculated, the encoder scale and the position scale, and everything sort of looks right. So let's go ahead and just key in 1200 by double-clicking on distance, typing in 1200 for 1200 millimeters, hitting enter, and let's see how many increments we get. All right, well, that looks almost right. We got 80,400. Now, as you recall from when we worked this out by hand with a calculator, we actually should get a few more increments. We're in the rough neighborhood, but we're not quite right. So this wouldn't be a super precision positioning operation, but it would be an okay one. Now, why did this happen? Why didn't we get the right number? Well, let's look at all our variables here. All right, circumference is obviously not too bad. We got 326.56 millimeters. Remember, we have kind of an imaginary decimal place 2 positions from the right. Our encoder scale calculated correct. It's still got a fractional component, 22,036.48. But notice when those two divided together, they were supposed to give us a position scale of 67.48. But if you divide this on a calculator by hand, what you'll get is 67.48. But remember, IPOS can't deal with that fraction, so it's just going to drop it. So the position scale was actually 67. And if we multiply 67 by 1200, we get 80,400, which is a little too short. We really needed that 0.48. What we need to do is we need to multiply one of our numbers by 100 again to get those 2 decimal places back. So we're going to just tweak our program a little bit to fix this, but you can see we almost got it right. So we should feel pretty good. And if you only got this far and this is what you got, that's not bad. That's an okay solution. But let's try to make it a little better. So I'm going to stop my program. And I'm going to go back into my code, and I'm going to do this. I'm going to take my encoder scale factor, and I'm going to multiply this by 100. And that's going to sort of add 2 more decimal places in here. Keep everything lined up. All right. And then we're going to have to divide that back out before we're all done. So I'm going to divide by 100 when we're finished. So we've sort of shoved it down another 2 places, and then when we're all done and we've calculated our increments, we'll take distance times position scale. We'll divide it by 100. It'll drop any fractional component, of course, and we should have just a nice integer increment count. So let's go ahead and recompile this thing. Okay, so we're now ready to try it again. So I'm going to click the lightning bolt. And notice that we've lost our variables watch window. It tends to duck behind the editor. So the way to get it back is to go to Window, find IPOS variables on the list here, bring it forward. And notice distance is still 1200, and look at that. We now have exactly the right answer. We have 80,976 increments. And you can see if you look at position scale right there, it now has 2 decimal places. It's got 67.48. So by adding that extra shift, we were able to preserve those 2 decimal places, and now we have a calculation that is a lot better. So that was challenging. If you got to the first point, absolutely that's good. If you got to this level and figured it out, even better. And that is the end of session number 6. This was a very hefty one. Math is a challenge, and I'm sorry about that. You probably want to go out and get some coffee now or something before you tackle the next session. Good job. Thank you for hanging through with this, and see you next time.